This video is going to go through an example of how to solve a parallel circuit. So we want to solve this circuit, which you have on your worksheet, problem number 1. So we want to solve for all of the missing components in our table. So to get our total resistance, we need our givens and unknowns. So what is unknown is the RT, and what is known is our R1 is 470 ohms, our R2 is 2.2 kilo ohms, or 2200 ohms, and R3 is 3.3 kilo ohms, or 3300 ohms. So we use our equation, which is RT equals 1 over R1 plus 1 over R2 plus 1 over R3. And once we plug in those values, we can sub and solve. I would find each of these individual ones on the bottom first, then add them all together in your calculator, and then do 1 over that answer. And once you do that, you should get around 346 ohms, or rounded to 350 ohms. So what is really important here to notice is that our total resistance now in a parallel circuit is lower than each individual resistance component. So resistor 1 is the smallest resistor, and that's 470, and our total resistance is even smaller than that. So in a parallel circuit, the total resistance is always smaller than every single component. So that's a good way to check yourself. If you are getting a resistance value that's bigger than any of these, you know you did it wrong. But in a series circuit, if you look back, the total resistance is always bigger than every single one because we're just adding them all together. So now we can find the voltage across each component, and we know in a parallel circuit the voltage total equals the voltage through each component. So we know that VT equals V1 equals V2 equals V3, and our total voltage is 15 volts. So for all of these voltages, we got 15 volts. Now we want to find the current through each component. So we have the voltage and the resistance of 1, of 2, and of 3. So for resistor 1, we can use V equals IR, and we rearrange it, so I equals V over R. And remember, these subscripts are just telling you which component we're looking at. So we're looking at the first one, so our 15 volts is going to stay the same for all of them. All we have to do is plug in our 470 ohms for resistor 1. We get 0.032 amps, or 32 milliamps, because we move the decimal place over 3 times. Now our second one, same exact thing. Our voltage is 15 volts. Our resistance is 2,200 ohms, so our resistance is 6.8 milliamps. And our third one, we can find the resistance to come out to be, the current to be 4.5 milliamps because of our 3,300 ohm resistor. And we can find the total in the exact same way, because we know the voltage of the total is that 15 volts, and our RT, which we found in the first portion, is 350 ohms. So we know that the total current is 43 milliamps. So now all we want to do is use Kirchhoff's current law to prove that we did the right thing. And a lot of you have said, why would we need to do this? We already found everything. But this is a really good way to check yourself, because if they don't come out to be equal, then you know you did something wrong, and you can go back and check it and not lose points because you got the wrong answers. So we know that the total current needs to equal the addition of all of them. So our total was 43 milliamps. Our individual currents were 32 milliamps, 6.8 milliamps, and 4.5 milliamps. You could also keep these in amps. They'll just be, the decimal place will be over three places. And now we got 43 milliamps equals 43.3 milliamps, and we just have that difference because of our rounding.